Dear students, welcome to the 13th online class of Control System Engineering. In last class we studied about underdamped second order system and their transient specifications, which include rise time, settling time, peak time and percent overshoot. In this lecture we will start chapter 5, which is reduction of multiple subsystems. Dear students, after this chapter you will be able to reduce a block diagram of multiple subsystems to a single block representing transfer functions from input to output, how to convert a block diagram to signal flow graph, and to find transfer function of multiple subsystems using Mason's rule. Dear students, now the contents of this lecture are equivalent systems, block diagram, reduction techniques, and various form, which includes cascaded form, parallel form, feedback form, and also how to move the block to find equivalent transfer function. Dear students, now we will start block diagram reduction. If you see the systems in real life, many of them consist of various subsystems, and each system have its own transfer function. In this chapter, we will consider how to combine these subsystems corresponding to a single system so that we can represent whole system with single transfer function. Students, if you see the first figure of the slide, that consists of various subsystems, which are G1, G2, H1, H2, and many more. These all subsystems combine to form a single system. These subsystems are represented by block. For this, we will find an equivalent system with which we will represent whole system in single block with input R of S and output C of S, as shown in second figure. Dear students, now we will start block diagram reduction. In block diagram form of representation, a system is represented by a block and signals, which are input signals or output signals. Output signals are represented by arrow. If you see the figure A represents input signal R of S and output signal C of S. These both signals are represented by arrow. In figure B, we have a system with transfer function G of S within the block, and input R of S is represented by an arrow, and output signal C of S is also represented by arrow. Students, in block diagram form we use a summing junction. This is used for addition or subtraction of various signal. In this we have one output signal and various input signal, and output signal is equal to sum or difference of input signals, and figure D represent a pick-off point. For a subsystems, sometimes same signal is required at various level. So for this, a pick-off point is used. With the help of same signal is made available at various level. If you see the figure, signal R of S is available at 3 different levels. Dear students, before starting block diagram reduction, we will study some common topologies used for interconnecting systems. And with these topologies, we will find equivalent transfer function or a single transfer function. The common topologies are cascade form, parallel form, and feedback form. Students, now we will study cascade form. When multiple subsystems are connected such that output of one system serve as input to the next, these systems are said to be in cascade form. Students, if you look at the figure, we have three subsystems, G1 of S, G2 of S, and G3 of S. Input of G1 of S is R of S and its output is X2 of S. And mathematically it is equal to product of G1 of S and input R of S. Now input of G2 of S is X2 of S and output is X1 of S, where X1 of S will be equal to product of G2 of S and its input X2 of S. So X1 of S will be equal to G1 of S, G2 of S, and R of S. Now this X1 of S serve as an input to G3 of S and output is C of S, where output C of S will be equal to product of G3 of S, G2 of S, G1 of S, and input R of S. Now rearranging the output equation, we can find equivalent transfer function which will be equal to C of S divided by R of S and will be equal to G3 of S, G2 of S, and G1 of S. And with this, we have reduced the system to a single block with equivalent transfer function G of S, which is equal to product of individual transfer functions of subsystem connected in cascaded form. And input is R of S and output is C of S. Dear students, second form we will study is parallel form. In parallel form, subsystems have common input and their output are summed together. In figure A, three systems are connected in parallel form, which are G1 of S, G2 of S, and G3 of S. All these three systems have common input R of S. For this common input, a pickup point is used. And output is sum of individual output of the system, which is X1 of S, X2 of S, and X3 of S. And for this summing purpose, a summing junction is used, and output equals sum or difference of X1 of S, X2 of S, and X3 of S. Now here we know that X1 of S equal R of S into G1 of S, X2 of S equal R of S equal R of S into G2 of S, and X3 of S equal R of S into G3 of S. Now substituting the values of X1, X2, X3 in output equation and taking input R of S common, with rearrangement we can get our desired transfer function for parallel form. If you look at the figure B, it represents equivalent single block diagram, which is equivalent system for parallel form. In this, transfer function will be equal to sum or difference of individual subsystems present in parallel form. And here it is plus minus G1 of S. This corresponds to first subsystem. Plus minus G2 of S. This corresponds to second subsystem and plus minus G3 of S. This corresponds. Students, now we will study feedback form. This form is mostly used in closed loop system to analyze output of the system. First figure represents all the components used in feedback form. Now we are trying to find single block transfer function for feedback form. If you look at the path from actuating signal, which is error E of S, controller G2 of S, and plant G3 of S, and then output C of S. This is known as forward path, and in this, controller and plant are connected in series. And if you look at the feedback path in this feedback system with transfer function G2 of S, output transducer with transfer function G1 of S are connected in series. So here we can use cascade form relation to find equivalent transfer function for both feedback path and forward path. For feedback path it is H of S, and for forward path it is G of S. And this is shown in second figure of the slide. Dear students, after reducing or applying cascade form, now we know that error is equal to input signal minus plus output of feedback system H of S, which is equal to C of S into H of S. And if you look at the forward path, we know that output C of S is equal to G of S multiplied by E of S. Now if you substitute error in output relation and with rearrangement, we will get our equivalent transfer function, which will be equal to output C of S divided by input R of S. And this is also shown in the figure. Equivalent transfer function is forward part transfer function G of S divided by 1 plus minus G of S into H of S. This product of G of S and H of S is known as open loop transfer function. Because if you disconnect the feedback path, it will become a single loop which will start with actuating signal E of S and will end on output of the feedback system. So in series form, this will be equal to G of S into H of S. Dear students, now we will study moving of blocks. For block reduction of a system, we have studied series form, parallel form, and feedback form. Sometimes subsystems are not arranged in the series, parallel, or feedback form. And for reduction, we require to transform given system in any of the given form. So for this purpose, we use moving of blocks across pick-off point or summing junction. Now we will study what rules are to be followed when we move a block to the left or right of a summing junction or pick-off point. First we will study these rules for a summing junction. If you look at the figure A, in figure A we have a summing junction with one input R of S and second input minus plus X of S, and its output act as an input to G of S, and output of the system is C of S. Now to move the system G of S from output to input branches, it will occur in all the branches of the summing junction. In this case, it will occur in RFS branch, and also in X of S branch. If you calculate the output, in both cases it will be the same. Now if you look at the figure B, in this output of summing junction is C of S having two branches. In one branch we have a system G of S and its input is R of S, and second branch signal is X of S. Now to move the block G of S to output, it will occur in the output branch, and also in the second branch X of S in reciprocal form to cancel out the effect, and net output will be the same. Dear students, now we will study moving of a system block across a pickoff point. If you look at the figure A, in this we have a pickoff point with input R of S and three branches. In first branch we have a system with transfer function G of S, and its output is R of S, G of S, while other two branches have output R of S. Now if we want to move the block G of S to the input side or left of the pickoff point, it will be present in input branch as G of S, while to maintain the output of other two branches, it will occur in reciprocal form in second and third branch. Now if you look at the figure B, in this at input side we have a block with transfer function G of S, and we want to move this to the right side of the pickoff point. And after the movement, this system with transfer function G of S will be occur in all the branches of pickoff point, and output in each case will be the same. Dear students, now with the help of example, we will study block reduction. In the given example, we have to find equivalent system with single transfer function for inputs R of S and output C of S. Now in the solution, as a first step, we will combine all the summing junction into a single summing junction. Dear students, now if you look at the system with a single summing junction, all the three feedback paths have common input and their output is summed. So this represents a system in parallel form. So for H1, H2 and H3 can be converted into a single system using parallel form with equivalent transfer function of H1 of S minus H2 of S plus H3 of S. Now if you look at the forward path, which includes G2 of S and G3 of S, these two systems are in series form, so its equivalent can be found using cascade form relation with equivalent transfer function of G3 of S into G2 of S. Dear students, after using parallel and series form, we get our reduced system. Now we recognize that our system is in feedback form. So applying the rules of feedback form and we get our equivalent transfer function. Now after reducing, G1 will be occur in cascade form with the feedback form subsystem. So equivalent system will be a product of G1 of S and equivalent system from feedback system. And equivalent system is shown in the second figure of the slide with input R of S and output C of S. Dear students, in the second example, we have to find an equivalent transfer function of the system in given figure. The system consists of various subsystems and we have to find equivalent transfer function. For system reduction, we mostly use series form, parallel form and feedback form. If you look at the right side of the system, we have subsystem G3 and H3 are present in feedback form. So for its equivalent, we can use feedback form. Now, if you look at the rest of the system, no apparent series, parallel or feedback form is present. Now to solve this, we will use moving of blocks across a pickoff point or summing junction. If you look at point V3, it is a pickoff point with two output branches. First branch have unit gain, while second branch have transfer function G2 of S. Now we will move G2 of S to the left of pickoff point. And to maintain the output, G2 of S will occur in reciprocal form in first branch. Dear students, first figure of the slide shows after using feedback form and moving G2 of S across the pickoff point. Now if you see, 1 over G2 of S is in parallel with a unit gain branch. So it will be reduced using parallel form. And in second step, G1 of S will be moved to the right of the summing junction to create a parallel form in the feedback path. And G1 of S will also occur in product with G2 of S. So here cascade form can be used. And these changes are shown in the second figure of the slide. Dear students, now after applying parallel form and moving G1 of S, you can see that two subsystems at the right side occurs in series form, where on left side, if we combine both the summing junction, a parallel form will be created, in which H2 of S or G1 of S will be in parallel to H1 of S. After applying these form, we will be having a system shown in the second figure of the slide. Dear students, after applying parallel form and series form, we have the reduced system in first figure of the slide. In this system, you can see that a feedback form occurs at the left. Now applying feedback form at the left, we get our system in series to the system at right side. Now we can use the relation of cascade form to find the equivalent transfer function of the system and can represent this system in a single block with input R of S and output C of S. Dear students, we can find an equivalent system of any system which consists of multiple subsystems using parallel form, feedback form, and cascade form. If any of these forms are not visible or prominent, we can use moving of blocks across pick-off point and summing junction. For this, you have to identify which movement of block is possible. Now, if any of you have any questions, please ask.